right, the formation of an ion, right, what is it that allows us to distinguish atoms from each other? So those are two questions I want you to think about. You can answer them in your notes, on your whiteboard, on a Post-it note, anywhere that's convenient for you. Good morning, Zoe.
No, it's just allergy. Their eyes were running itchy.
Okay. Okay, so here's what we're gonna do, and I think this will help us as we move forward. I want you to think about the way that we have encountered atoms so far has really been thinking about their atomic number, and that's what's going to be most useful to us here. So if you're thinking about an example, say for instance, calcium, right? We could look on the periodic table and find calcium's atomic number, right? And then we might be able to say something about the number of electrons or the number of protons that calcium has based on the information that's found in the periodic table. So I want you to take maybe, let's say 2 minutes and see what you can do in terms of this table and filling in the information for these columns and rows. And see if you can do maybe 2 complete rows or 2 complete columns. Okay, so as we're thinking about this, I'm going to give you some examples that we're going to take a look at. So if I scroll down, you can see some of the examples that probably you were working on yourself. And so the reason why we're doing this as a review is twofold, right? The first one is I really want you to think about this idea of what electrons are and how they impact atoms. But the second piece that I want you to be attentive to is the fact that the combination of these two, right? There's usually ratios, just like we think about coefficients in terms of balanced equations. The ratios that we're going to see, for example, between a cation and an anion is going to depend upon their respective charges. That's going to be something that's super important for us as we start to think about electron configurations of individual atoms, because that's going to help us understand how they react with other atoms. So for example, the reaction between a cation and an anion is going to be something that's somewhat dependent upon their individual electron configurations. So before we move on, I want to talk about some norms. So this is a new normal for us, right? And new normal is, right, the virtual learning environment. And so there are a couple of ways that you can engage in this environment. You can unmute yourself to ask a question. Those are always welcome. I love it when you ask questions, and I really hope that you will. But if you're like, I don't really want to speak right now, the other thing that's really cool about this is you can go up and in the chat box, right, you can type a question here too. So if there's something that you want to ask, but you don't want to unmute yourself and ask that question, you can absolutely do that here. So for example, right, if you're not certain about whether or not you would have the right answer, you're always free to ask. Right? And I will do my very best to be responsive to the chat box. I'm learning to look in 3 different places at once, so if I don't get to you right away, just hang on, be patient. I promise that I will get to you as soon as I see it. So thank you for your patience with me, especially as we're learning new things. I really appreciate it. Okay, if you're like, whew, all right, I'm good to go, I know how to do this, great. Then we will move on, right? And you can do additional practice if you feel like you need to. If you're like, ooh, I'm not sure if I've got this, I think I need a little bit more practice, then I'm happy to stay and have conversation with you in the virtual office hours after class today. Or if you're thinking, that doesn't work, I need lunch, I'm hungry, then you can totally connect with me after class. We have another office hour period from 2 to 4 today. So you've got lots of choices in terms of how and when you connect. And if those times don't work for you, you can always just send me an email. The really lovely news is that because we're virtual, we'll have plenty of opportunities to connect. So whatever you have questions about, you'll always have the chance to ask. Okay, so if we're thinking about how we take this information and make sense of that, I want to connect us with a really cool resource. So if you haven't seen a flame test, they're just beautiful to observe. And so I wanted to make sure that we had an opportunity to see what happens when we excite electrons, because the color change is really astounding. It's very compelling. So here we go. I want to show you an example of what that visual looks like. So I love fireworks. It's probably one of my favorite things. And so I wanted you to be able to see why we have the colors that we do associated with metal ions. So for example, here, right, there's our metal ion and its flame test color. And the really cool part about that, right, the extent to which we see those colors is all about excited electrons. So I want you to take a moment and see if you can recall from the video, right, what were the colors that you would associate with sodium or strontium or copper or barium? And while you're thinking about that and doing a little bit of brainstorming, the whole idea behind a flame test is that, right, we're either going to be absorbing or emitting light. So if an electron is moving to an energy level, whether that's higher or lower, we're going to see something about whether or not we absorb or emit light. And so there are a couple of ways we can do this. The video that you saw just had kind of tea lights that had been emptied out that we filled with metal salts. But you could also do this using a Bunsen burner. So a Bunsen burner is one of the tools that we see in a chemistry lab. And so you have air that we add here. There are holes. And then you have gas, that's usually the fuel that you add. That is what we have in part B. And so if we're thinking about then our flame, right, and what's hottest about our Bunsen burner, we can actually see that here. So you're gonna love my Bunsen burner flame. So air is what we're adding at part A, gas is what we're adding at part B. And so the whole idea here is that when we emit light, right, so we shine out light when our electrons move back to a lower energy level. So Raquel asked a really insightful question before we got started today about how, right, how electrons move to excited states. And so we move electrons by putting energy into a system. And then the emission of light is when those electrons relax back down. And so if we're thinking big picture, right, about why this matters, well, it matters, right, because of fireworks and all of those beautiful colors that I love. It matters, say, for example, if you look into a fire, whether that's a fire in a fireplace or a campfire, and you notice the different colors in the flames, those are the result of different metal ions, right, emitting color. And then it also matters for other phenomena. So I think this is one of the coolest phenomena that I've come across recently. So this is a high resolution image of the sun. So this is the light that the sun emits. But I want you to think about this. There are, right, these dark bands that you can actually see. And so what are these dark bands? Well, if we think about the idea of the sun and the light that it emits, everything that we see here color-wise is the result of elements. Elements that essentially are exciting electrons, and then when they relax back down, that's how the light gets emitted. And so what's really cool about that is that a spectral line is a little bit like a fingerprint. So we can use spectroscopy to be able to identify atoms, elements, or molecules that are present even millions of miles away. So if we can see the light, we can actually see what the composition of stars are. Or if we, say, for example, are looking at another galaxy and we see the color of light coming from stars in that galaxy, we actually can determine, based on two types of spectral lines in the electromagnetic spectrum. So emission lines, those are the colored lines that you saw on the previous slide. They're specific wavelengths of light that are emitted by a source. And then the absorption lines are black lines that are a result of the wavelengths of light being absorbed along the line of sight. So one of the things that is useful for you to think about is whether or not light is being absorbed or emitted based on what you can see. So one of the things that's really cool about this, and you could explore this further, is there are spectral lines and the sun spectral lines, and then NASA actually has some really cool videos about measuring the universe in spectroscopy. So if you love studying the cosmos and thinking about the way that we can study stars that are millions of miles away, then this is right up your alley. I had a great question from folks about the PowerPoint. So I should say I will post this PowerPoint with my notes in it, as well as a recording of our Zoom session to iLearn at the end of this session. So if you're like, ooh, I want to capture those notes, I will make sure that they are available for you. And I will post a PDF so that you have access to that once we get started on our next activity. So here's what we're going to do today. We're going to look at the periodic table in a new way. And the way we're going to take a look at that periodic table is we're going to start to think of it in terms of electrons and their orbitals. So if I think about this, right, I have this left-hand block. These are the alkali and alkaline metals. This is labeled as 1s, 2s, 3s, 4s, 5s, and so forth. So these are what we think of as the rows in our period. You'll also notice that, right, the p orbitals are on the right-hand side of the periodic table. That's super helpful because these are our nonmetals. And then 3D and 4D are what we think of as our transition metals. I want you to notice that most of our periodic tables put helium over here on the right-hand side because it's considered a noble gas, but it's also a 1s orbital. So if you wanted to, you could move it over to this side. So I want you to think about the periodic table as a visual way of organizing elements by orbitals and energy. So take a moment and in your notes, go ahead and sketch this version of the periodic table. That's going to be really helpful as we move forward, especially when it comes to writing electron configurations. And while you're doing that, I will post a PDF of these notes in iLearn. Thank you for your patience. I feel like one of the things that's exciting about this new adventure is learning how to do new things. At the same time, I appreciate the fact that learning to do new things can sometimes, right, take a couple of iterations until you get it down to the format or the procedure that you think would be most helpful. So let me go ahead and to our notes, add a PDF of the lecture notes you're going to see. That way, if you're taking electronic notes, you'll be able to take the notes directly on the PDF. So give me 2 seconds. And that should be up and available for you. I meant to do that this morning, but then I got distracted because I was so excited to see folks again. It's so funny. Last week was really weird not to have class. All right. So here we go. All right. Thanks for your patience. We should be good to go. Okay, so if you check the iLearn page, there should be a posted PDF file of the notes. Cool. All right. So if I'm thinking then about how we take this information in terms of our new way of looking at the periodic table, we're going to start to think about how we write electron configurations. So one of the resources that we're going to use to do that is a PDF that was in the email from me. So if you take a look at if you take a look at the following, then here we go. So this is the practice sheet that we did. The next one should be this. So this is from email from me, or you can also find it in iLearn. And I have these broken out. So this is the worksheet that you're going to be working from. If you don't have the opportunity to print these, that's okay. You can just do them in your notes. Part of the reason why I wanted you to be able to see that was the following. So when we draw out our electron configurations, we can do that using boxes or squares or circles. It doesn't matter which one we use. I've shown circles here, but if you take a look at my screen, right, squares are fine too. Doesn't matter what you use. That's a great way to be able to represent the orbitals. So whether it's a circle or a square, this is what we think of as the space where electrons go. And the reason why that matters is because we're going to start to think about how we organize our electrons. So let's take a look at an example. So here we've got argon. So argon is a noble gas. You'll find it on the right-hand side of your periodic table. And when you're looking at argon, I want you to think about the number of electrons that argon would have. And then I'm going to give you a couple of rules that we're going to use. So the first rule that we're going to use is that you always put individual electrons in before you pair up in an orbital. So for example, the first 2 electrons will go in one s, and you always fill 2 electrons per every orbital. And then the other piece that is another rule that's important to know is that you always pair them up and down. So we use up and down arrows to represent the spin of electrons. So you're going to have 2 arrows, one up, one down, and those single-headed arrows, so they only essentially have one side of the arrow, is what we use to represent electrons. And so if we think about how we fill in electron configurations then, The way that we do this is actually by looking at the number of electrons and where we put them. So the first rule is that we always put 2 electrons in every orbital. The second rule is that because of what a property of electrons we call spin, one of the electrons has to point up and the other electron has to point down. Then the really cool part, right, about this is that we take the total number of electrons that we have, and we place them. So let me show you an example of what that looks like with argon. So here's argon. We know that it has 18 electrons because of its atomic number. And so if I take a look at argon, here are the features that I want you to see in terms of filling in the orbital chart. Do you notice how there's one arrow, right, pointed up and another arrow pointed down? So if we count these, right, 2, 4, 6, 8, 10, 12, 14, 16, 18, we filled all electrons in our orbital diagram. And what's important about this is that you're going to notice that there's some spacing between these orbitals. So the letters 1s, 2s, 2p, 3s, and 3p refer to the relative space on the periodic table. So if we think about it, right, the first row on our periodic table would be 1s, second row on the left-hand side would be 2s, third row is 3s, right? And then P is what we see on the far right-hand side. So since argon has 18 total electrons, those electrons are going to be spread out both in space and they're going to have different energy levels. And so that's really what this electron orbital diagram represents. Now, you can think of this a slightly different way. So if I were to draw what an atom of argon would look like, I would have the nucleus in the middle. And so in that nucleus, I would have 18 protons, 18 neutrons. But then around the outside of my nucleus, I would have the first shell, or what they call subshells, which would have 2 electrons in it. And they always have 2 in that first shell. And then all other shells have 8. So because argon has 18 total, it would have 3 subshells. The first shell has 2 electrons. The second shell has 8 electrons. And the third shell would have 8 electrons. Now here's the really cool part about argon. So argon is a noble gas, right? And what does that really mean? Well, it means that it has a completely filled, what we call octet. So because that outer shell is completely full, it's satisfied. It doesn't want to give up electrons. It doesn't want to gain electrons. It's completely satisfied as is, which means that it's fairly stable. The really cool part about this is that because argon is one of the most abundant gases that we have in our atmosphere, it's good that that's stable. We want stable. Stable is desirable. But this is super interesting. It's the third most abundant gas in Earth's atmosphere, but it makes up less than 1%. So how else might we represent the electrons in our orbital diagram? One of the ways that we can do that is through writing out an electron configuration. Now, if you're wondering how you would do this, you're going to look at your periodic table and you're going to literally go across atom by atom and fill in the electrons. So for example, 1s2 represents hydrogen and helium, the electrons, the first 2 electrons that we have in our periodic table. 2s2, if we're thinking about our periodic table, right, what are the electrons there that would represent? Right, so if we're thinking about that in terms of our periodic table, right, what electrons does that represent? And so if we're looking at a periodic table, we should be able to count all the way across to be able to find, right, the representation of our electrons. So 1s2, 2s2, 2p6, 3s2, 3p6. And here's how you know if you set it up correctly. If you add up each of these superscripts, so 2 plus 2 is 4, plus 6 is 10, plus 2, right, is 12, plus 6 is 18, that's the total number of electrons that argon has. This process is kind of long and tedious. So if you're thinking about the long form of this, you can imagine that if, say, for example, you had to write out the electron configuration for lead, you would be like, oh, that's tedious. So we actually have a shorthand version that we use to abbreviate it. And this is the electron configuration that you're going to see most commonly used. And it's the one, say, for example, that I will ask you for, especially when we're looking at larger, heavier elements. So how do we do that? Well, we use these square brackets, and we use the gas that is the noble gas that precedes whatever that element is on the periodic table. So if I'm looking at the periodic table and I'm looking at argon, the gas that's right above argon in the periodic table is neon. And so neon is what I put in my square brackets. That's my noble gas. And then I use the next row. So the row after argon is row 3, right, is what I'm looking for, right? Because I'm trying to get 2 argon. So 3s2, that's sodium and magnesium. And then 3p6, those are the electrons from aluminum, silicon, phosphorus, sulfur, and chloride. And then ultimately, the 6th one here is what makes argon. Yep. So Julian's right. If you know how to write out the short version, you are great to go. So I think it's important to look at another example. And so I want you to take a look and see if you can do the following. So this is the next example in that sheet. And you can do this on your whiteboard. You can do this in your notes, right? If you're doing electronic notes, you can do it that way too. You can do it on the printout. So go ahead and take a moment and see if you can do both the orbital diagram, which is what we see up here, and the electron configuration, which is what we see here for magnesium. So I had a couple of really great questions. So if you are thinking about the placement of the arrows, someone was like, hey, does it have to be up or down? How do you know? And the answer is, as long as you have one up arrow and one down arrow, right, then you're good to go. And then I got another question about how do you determine how many circles for S and P? So S is always a single circle. So 1S will only be one circle. 2S will only be one circle. S is always only a sphere. P typically has either 3 circles or 3 boxes. And the reason for that is because P can have 3 different orbitals. Again, that orbital refers to the shape, or another way of thinking about that is the electron density or its position in space. And so the answer really is, if we're thinking about p orbitals, it should be 3. If we're thinking about d orbitals, it should be 5. And if we're thinking about f orbitals, then it will be 7. And so if we think about the number of electrons then that would fit, that should be 14. So if I draw out my options, I can label that then the following way. And I'll put an example up using my whiteboard for you to see. So S always has 1. P always has 3. D always has 5. And F always has 7. So if we're thinking about that, right, this is the number of orbitals for S, P, D, and F. So the purpose of the orbital chart is really to help us make sense of how many electrons we have and what kind of energy they have relative to each other. And so if you're like, why do I care about the orbital chart? The answer is you care about the orbital chart because we're going to use that chart to determine the number of valence electrons that we have. So we're going to start by building up with our stable states of atoms, and then we're going to start to think about what happens if we have ions, and then we'll be able to think about how those atoms or ions might react through their valence electrons with other atoms or ions. So hopefully you've had a chance to try out this guy. Take a moment and take a look at what you have. Okay, so now that you've taken a look, here's what I want you to see. Do you notice how the long configuration matches what we have drawn here? So if I have a total of 12 electrons, my first 2 electrons go here, my second 2 electrons go in the 2s, and then my next 6 electrons fill up the 2p, 2 electrons at a time, and then my last 2 electrons fill up the 3s. Now that's, right, a lot of writing to do, so we can shorten that and just say, hey, look, this is neon, right? All of the electrons up to neon plus the 2 electrons in the 3s2. And if you're thinking about that in terms of what that might look like in terms of your electron diagram, you could also draw it this way as well. So part of what I want you to think about, right, is how to draw each of these 3 representations. So let's do a quick review of how to do that. So right now, I don't care about what's in the nucleus. You can just draw a circle and label it as nucleus. The first shell outside of that nucleus will always have 2 electrons. Every other shell can hold up to 8 electrons. So for example, if I had 10 electrons, then I would have 2 shells, right? In this case, because I have 12 electrons, I have to start another shell and put 2 of those electrons in that shell because I've already filled up the other shell. So I think that one of the pieces that are really helpful for you to think about is how you put the electrons. Because we don't actually have enough electrons to fill the 3p section. So right now, 3p is going to be empty because we only have 12 electrons, right? So Alec and AJ were both right. Each arrow represents 1 electron. And so if you're trying to make sense of, right, which electrons go where, you're always doing one electron at a time, right? So 1 electron, 2 electron, 3 electron, 4 electron, all the way up to 12 electrons. I had somebody ask, does the arrow have to be facing up and then the arrow on the right facing down? And the answer is no. You always have to have at least one up and one down arrow, but you could start down and then go up. It wouldn't matter. So another great question is the identity of the ion that goes here is always going to be based on your periodic table. So in this case, if you're looking at a periodic table for magnesium, right, you're going to look at what is the noble gas that's just a row above. So you're going to find wherever your atom is and then go a row up, go all the way to the right-hand side and figure out what the identity of your noble gas is. So the idea here is this square bracket says, okay, everything up to, right, this element, in this case neon, right, I'm representing in a shorthand or a short version. So whatever the noble gas configuration is for neon plus 3s2. And so that is the way that we do a short version, is essentially it's easy to find the noble gas because it's on the right-hand side of the table. And then, right, I'm able to, right, just add whatever the additional electrons are, right, after that noble gas to get to the desired atom. Okay, cool. So here's what I want you to do. There are, I think, let me double check, at least 3 other ones for you to practice. So I want you to try doing at least one on your own. And if you get stuck, go ahead and send me a note in the chat box and I'll answer any questions. So we've done the first 2 so far on this one. Try out nitrogen on your own. See if you're comfortable doing that. And if you get stuck, just send me a note in the chat box. So let's think about what nitrogen would be. If I'm looking at the periodic table for nitrogen, right, and I'm thinking about the total number of electrons, right, how many electrons does nitrogen have? Well, it should have the 2 electrons that make up hydrogen and helium, plus the electrons for lithium and beryllium, plus the electrons for boron, carbon, and then nitrogen. So that adds up to 7, which means that I should have 2, right, 2 electrons in the 1s orbital, 2 electrons in the 2s2 orbital. And then if I think about that, right, that's 4 total. So then in my 3p, I should have a single electron for each one. So I think one of the things that's useful to make a distinction here is that you have the number of electrons. There are always 2 possible for each circle, and then the number of orbitals. So an s orbital, there's only ever one s orbital, right? They're single by themselves. P's, there are always 3 p orbitals. There are 5 d orbitals, and there are 7 f orbitals. And so each of those can hold up to 2 electrons. But here's the other rule that we're going to follow. We always put electrons in for each level singly, and then we pair them up. So for example, if I only had 2 electrons, then I would have a pair. But if I had 3 electrons, then one of those electrons would be by itself as a single. If you're like, hey, I'm not sure about that, I think I could use a little bit more help, I have some additional resources for you that I think would be super useful. So I want to show you those just for a moment. So if you go to the learning plan that I had for us, there's a really awesome video on how to do electron configuration. And so if you're like, hey, I think I need a little bit more support here, this is a great resource for you. I highly recommend it. And then the other space that you want to take a look at is chapter 6.4. That's another space that will be super useful for you as you're finishing up thinking about chapter 6 and that first page that we've been practicing. Okay, so we're going to do a little bit more practice with this. If you get stuck, don't worry. There will be other opportunities for us to come back and make additional sense of it. So here we go. Here's what I want you to see. Okay, when we're doing our electron configuration, sometimes there are some elements that don't follow the rules. There are exceptions. And so I'm not going to expect you to be able to write out these exceptions. They're going to be information that's given to you. So for example, you're not going to see one of these 2 exceptions on an exam. Instead, I want to show them to you to give you an example of why sometimes there are exceptions to the rules. So if we're thinking about filling in the orbital diagrams for the elements copper or chromium, I want to show you why those electron configurations are going to be a little bit different. So these are exceptions to the electron configuration. Here's what I want you to see. The argument is that we always make choices about where we put electrons based on stability. And so the idea here is that something is more stable if it's half filled or completely filled than if it's only partially filled. So the idea here is that electrons sort themselves into orbitals. And a good way to think about an orbital is just it's the place where we're most likely to find an electron. So you can see here the 1s2 has 2 electrons, the 2s2 has 2 electrons, and these are great, right? They're full, they're satisfied, they're relatively low energy. And that's the same for the 2p, for the 3s, and the 3p. But then, right, we get up to the situation where we have a 4s and 3d. And if you were to think about copper, you might think that you would write it as 3d9, 4s2, right? That might be your preference for how you would write it. But in this case, it actually is better to write it as the s orbital being half filled and the 3d orbitals completely filled, because that leads to a little bit more stability. So this is the electron configuration for copper, right? 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s1. So it's up to you whether it's the up arrow or the down arrow that you write singly. It doesn't matter, because in this case, you're going to laugh at this, we don't actually know which one it is yet. This is a great example of how there's still a part of the scientific theory that we don't know. And so when we refer to electrons in terms of spin, other than doing the experiment, we don't actually have a way of knowing whether it's an upspin or a downspin. So it doesn't matter whether you write up first and then down, or down first and then up. Either way is correct. So you don't have to worry about that. What's super interesting about this to me too is the reason why they say that they have to have opposite spins actually has to do with the fact that no two electrons can be in the same place at the same time. And so the reason they refer to spin, right, is because they know that electrons pair, but they also know that electrons can't be in the same place at the same time. So using an up arrow and a down arrow is the way that they represent electrons being in proximity to each other, but not in the exact same place at the same time. So here's another example, the chromium example. And so again, I'm not going to ask you this on a quiz or an exam, but I'm showing it to you because I think this exception helps illustrate why we write orbital diagrams the way that we do. So if we look at chromium in terms of its place on the periodic table, there are a couple of things you're going to notice, right? Chromium, if we're looking at the periodic table, is where? It's going to be, right, in the transition metals. Right? And so if we look at copper and we look at chromium, right, they're both in transition metal territory. So we know that transition metals are going to behave a little bit differently. And that's okay. It's cool that they do that because that's part of the reason why we get some of the most brilliant colors in terms of fireworks. But it's important that we understand why they might behave differently. And so in this case, chromium is a really great example of why we have singly paired electrons. So for example, right, because of chromium's position, right, everything is paired up until we get to the 4s1 and the 3d space. And you're like, okay, well, that's good. I can see how I pair up each of those electrons, but how do I know when to put single electrons versus paired electrons? And the answer is you always have to put in electrons singly before you can pair. And so in this case, rather than taking this one electron and pairing it up with 3d, we actually keep it by itself where it's a half-filled orbital, because all of these are half-filled, and that makes them just a little bit more stable than if they were completely full. So these are exceptions to the electron configuration rules, and there aren't very many of them. In fact, if you look at your periodic table, the only ones that are exceptions, right, are chromium, molybdenum, right, everything that's in that row, and then what's in the, what's in that column. So the column of chromium, molybdenum, and tungsten, and then what's in the column of copper, silver, and gold. And so what's really interesting about this is that, right, the 4p doesn't have anything because we don't have enough electrons to fill up the 4p. So again, when we're filling out our orbital diagrams or our electron configurations, we can only place as many electrons as we actually have for that atom. So for example, right, if we think about the number of electrons that copper has, right, it has 29 electrons. How do I know that? Well, a couple of ways. I can add up my superscripts. That's one way to know whether or not I have 29 electrons. Or, right, I can actually count them by twos. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 29. So you guys are doing a great job making sense of this. And I have a couple of comments in response to your questions. So when we're thinking about the exceptions are the two columns that begin with copper and begin with chromium. So if you're looking at your periodic table, you can just circle those and put exceptions to the electron configuration. The lovely part is you're not going to have to answer those on a quiz or an exam. I just use them to illustrate or highlight the rules so that you can make better sense of them. Thanks, Abigail. Column 6B and 11B are a great way to orient folks to those atoms. So when we're thinking about filling in then electrons, right, you always start at the 1s level and then you fill up. So it's a little bit like entering a hotel. You always enter the hotel at the ground level, and then you can travel up to additional floors from there. Okay, so there's some opportunities for you to practice writing out orbital diagrams and electron configurations on that worksheet. We're going to take our time and do a little bit more practice now. So if you want some assisted practice, the first worksheet, right, 6_1 is the space where you're going to have a little bit more support. So now we're going to take a look at how to do this. Say, for example, if we had to do it on a quiz. So this is the structure that a quiz would look like. So I might ask you, how many electrons are in an arsenic atom? And then I'm going to ask you to draw the orbital diagram for arsenic. And then I want you to think about which ones would make the valence electrons. And no, there are not. So the rules for 8b would be the same, because in this case, there's not enough gain in terms of the change in stability. So delightful news for you is everything that we're doing right now in terms of electron configurations applies to everything that's in the periodic table except for columns 6b and 11b. So let's take a look at arsenic. Where would you find arsenic on the periodic table? So if you find nitrogen and you look below it, there should be phosphorus and then there should be arsenic. So there should be 33 electrons for arsenic. Let's see if you can draw an orbital diagram for arsenic and what it looks like. All right, so I'm trying to find our periodic table so I can give you the right reference. Oh, here we go. Hooray. Yep, so column 6b and 11b are the only columns that you have to worry about. So if you're looking for arsenic, Abigail's right, you're looking at column 5a. So take a moment and see. Yes, oh, you are so smart. Mackenzie Hansen, kudos to you. The valence electrons is equal to the, it's not the atomic number that it's equal to. In this case, the number of valence electrons is going to be equal to its column. A good way to think about it is typically its column number, but I can show you an example of how you're going to find that in just a moment. So here we go. Let's scroll down for a minute. All right, so we know that we have 33 electrons in an arsenic atom. And so if we think about drawing our orbital diagram, notice it doesn't matter whether you draw square boxes or whether you draw circles, it's the exact same thing. Some textbooks use squares, some textbooks use circles. I want you to feel comfortable using either one. It doesn't really matter. So squares or circles, we fill up from the bottom to the top. We always pair at each level. So I put in my first electron, then my second, first electron, then my second, all the way up until I've completely filled my 3D. Then if I take a look, I'm going to fill my 4s and my 4p. So whatever the highest number is that are filled, those are going to be my valence electrons. So nitrogen in this case would have 5 valence electrons. So its column number is equal to the number of valence electrons. So if you're thinking about this, you're like, oh, wait, how do I find this? Where do I find this? Right? Your number of valence electrons is equal to what's called the group number. So if you look at the top of your periodic table, right, at the top of each column, there should be a number. If you're trying to figure out the number of valence electrons, say, for example, the number of valence electrons that nitrogen has, you can look at that group number, which in this case is 5, and that tells you the number of valence electrons. So what's really cool about this is if you're thinking about the number of valence electrons, that's going to be the number of electrons that are available to react with any other chemical that's out there in the world. All of the other electrons are what are considered core electrons. They're protected, or another way of thinking about that is that they are attracted strongly to the nucleus, and it's really just the valence electrons that are available and reactive. It is the number of electrons that is in the outer shell. So literally, it's what you think of as the outermost electrons, or the electrons that are most available to interact with the world. So whatever else is out there in a system, that's the reason why you're going to see them. So Summer had a great question about why we don't have paired electrons in 4p. And so this is one of the rules. We always fill each orbital with individual electrons before we can pair. And so if you're like, wait, what's that rule? We have the Aufbau principle, which is I always build from the bottom up. We have Hund's rule, which says, look, I always have to fill singly before pairing. And then the other one that we're going to think about is the fact that, right, these slight differences in terms of height, say, for example, in terms of the way we fill, means that 4p is the most energetic out of our electrons. 1s is the most stable. That's because 1s is the closest to the nucleus, and 4p is the farthest from the nucleus. So when we think about our valence electrons, those are the electrons that are open and accessible, right, and can be grabbed. And so these single electrons have to individually fill each orbital. If we had more electrons, then we could pair them up. But in this case, because we only have 33, we have 5 valence electrons, 2 of which are paired, 3 of which are single, which is really cool then when you think about a molecule like ammonia. Ammonia is NH3. It has a lone pair, 2 electrons, and then it has 3 bonds to hydrogen. So that's a great example of why nitrogen forms the molecule ammonia, because it has 5 valence electrons, 2 of which form the lone pair, and then 3 of which form the bonds to hydrogen. Okay, let's take a look at another example. Let's take a look at the electrons that are in a copper atom. So remember, this is our exception to the rule. And this is important because transition elements have a different way of behaving in terms of their valence electrons. So I want you to see what that example looks like as the exception. Remember, don't panic. This is not something I'm going to ask you on a quiz, but it's important for you to see the exception so you understand why we use the rules the way we do. So if I'm looking at my number of valence electrons, right, copper has 29 electrons. And so this is, right, my orbital diagram, and I completely fill my 3D orbital, right? So everything is paired together. And then the only one that I have left is my 4s, and that's a single electron. So copper only has 1 valence electron. So the most likely ion that it will form is a copper +1, where it's given up this 1 electron because it's unsatisfied. It's single, it's by itself, right? Whereas everything else in the 3D, 3p, 3s, 2p, 2s, and 1s are all paired and satisfied. They have a lower energy level than a single electron that's by itself. So if we're thinking about then our transition metals, part of the reason why we have this rule, right, is because it means that This electron configuration makes copper just a little bit more stable, and stability really drives everything that we do in terms of chemistry. So there's the exception to the rule for copper. Here's what I want you to do. We're going to take a look at this now with respect to families. So a family is a group of atoms that have similar types of behavior. So take a look at your periodic table and find oxygen, sulfur, and selenium. If you're trying to figure out where that is, you can totally help somebody out by posting in the chat box where you would find these, what's the group number for them. Awesome. Thank you very much. So if we're taking a look at 6A, so the question in terms of why copper is an exception, I'll go back to that in just a minute. For now, hold that thought and focus on oxygen, sulfur, and selenium. And then we'll talk about why we have exceptions to the electron configuration. So go ahead and take a moment and think about the pattern. What do you think you would see as a pattern for oxygen, sulfur, and selenium? So if we think about where they are, they're all in the same column in the periodic table. And so if I think about how I would fill them, oh, thank you. They have the same number of valence electrons. That's awesome, Amber and Heba. Thank you so very much. So here's what I want you to see. This is what is so cool about chemistry. Do you notice now, right? They all have the same pattern. Here's why that's beautiful. If you know the pattern for one, then you know what the pattern is for everything else that's underneath it in the same column. So really, all you need to do is think about what the electron configuration is across the top row, and you know what the number of valence electrons are for everything else that's underneath it. Notice, right, these are the valence electrons. Oxygen has 6 valence electrons. Sulfur has 6 valence electrons. Selenium has 6 valence electrons. The only thing that changes is the number of the row. So in this case, this is the second row. In this case, this is the third row. And in this case, it's the fourth row. So oxygen, oxygen, sulfur, and selenium all have the same structure. The only difference is the noble gas that you use for the electron configuration is whatever noble gas is at the end of the row, just above the position, right? And then it's just the number of valence electrons. So you can do shorthand really quickly now. If you know the number of valence electrons, you can write that out just based on knowing the number of the row. And then if you know the noble gas that's closest to that atom, you can write your electron configuration in no time at all. So if we think about this, right, our total number of electrons, right, should be equal to the sum of the superscripts, right? So 2 plus 2 is 4, plus 6 is 10, plus 2 plus 4, that's 16. It's a total of 16 electrons. So that's how I check to know whether or not my long configuration is correct. How I check to make sure that my short configuration is correct is I find sulfur on the periodic table, I go one row up all the way to the right, and I see that neon is the noble gas. So that's the correct gas to go here. And then the only electrons I have to worry about are the electrons that are in the row of that atom. So 3s2, 3p4 is what gets me up to sulfur. I think this is a really great example of the reason why we care about electron configurations, because oxygen, sulfur, and selenium are all going to behave very similarly because of the number of valence electrons that they have. Okay. So we're going to wrap up today's class by thinking about how our electron configurations are going to influence the behavior of a molecule. So before we do that, we have to do a little bit of thinking. So ionization energy is the energy that it takes to pull an electron away from an atom. Here's what I want you to think about. If we go back, say, for example, to magnesium, here's what I want you to see. So if you're thinking about magnesium, if everything is stable when it's completely filled, what would make magnesium more stable? The idea here is if you lost this 2 electron, and it's actually easier to see here, these 2 electrons are this outermost shell. Those are the 2 electrons that are easiest to lose, which is why magnesium forms a 2+ ion. It loses these 2 electrons, still has everything that's completely filled, and so that's the more stable ion to form. And so the reason why we form the ions that we do is all because of their electron configuration, and specifically this idea of having completed shells. So the first shell is always 2, and every subsequent shell after that is 8. And so because this shell only has 2, it's a lot easier to lose 2 electrons than it is to gain 6. So that's the reason why magnesium forms a 2+ ion. So we're going to take that information then, and now we're going to apply it. We're going to make sense of other pieces of information that have to do with what we call periodic trends. And so we're going to start here and finish up this part of the conversation on Wednesday. So this diagram shows you the ionization energies, or the energy it takes to pull off an electron, for the elements from lithium all the way up to neon. So here's what I want you to think about. The energy here increases as we go up to neon. So if you're looking across the row in the periodic table, why is that? Why is the energy for neon so high? Think about that for a minute. Well, if you're thinking about the electron configuration, what's true about the electron configuration for neon? It's completely filled. Does it want to give up any of its electrons? Right? The answer there is no. It's super stable. It has an octet. So because it has that octet, it's stable, and so it says, nope, sorry, you can't have them. I want to keep them. That's why the noble gases are so stable. But what about lithium? Right? Think about the electron configuration for lithium. Lithium only has to lose what? 1 electron. Lithium only has to lose a single electron. And so if we're thinking about this in terms of why there's an increase in the first ionization energy from lithium to neon, right, is, so Mackenzie's question is a really good one. She says, what is there would have been 4 electrons on magnesium? Like the number of electrons are the same number when gaining or losing? So in this case, right, magnesium only had 2, so it was obvious that that was what it needed to lose. But I think Mackenzie's asking about a case like carbon, right? Well, in the case of carbon, carbon doesn't form ions, right? Carbon already has 4 electrons, and it wants 4 more electrons. So what do? Well, in this case, carbon is going to form covalent bonds because it doesn't want to give up its electrons, but it does want to gain electrons. So what it does is share those electrons. So a great way to think about whether you're forming ions or covalent bonds really depends on the number of electrons you have to gain or lose. Anything that's in the middle is going to have this tendency to form covalent bonds instead of ionic bonds. So if you're thinking then about going back to this question of why is there an increase in the ionization energy from lithium to neon, here's what you would say. Something like, as you move across a period, or as you move across a row in the periodic table, there are more protons that are in the nucleus. That increase in the nuclear charge, right, increases the attraction for the electrons in the shell. So the more charge in the nucleus, the stronger it pulls on the electrons. So neon, right, because it has the same number of protons as it has number of electrons, there's a lot of nuclear charge that's pulling on those electrons. And that's really what makes neon more stable, less likely to give up its electrons. If we think about the next question, so why is the energy of pulling an electron off of boron lower than that of beryllium? This is where it goes to thinking about our orbitals. So the electron that we lose from boron is from the 2p orbital, whereas beryllium is going to lose an electron from the 2s orbital. It takes less energy to remove an electron from the 2p orbital because it has a higher potential energy. So if you wanted to double check and make sure of your reasoning there, you might draw out the orbital diagram for boron and the orbital diagram for beryllium to check and make sure that you were filling the electrons in the right orbitals. So any element that has more than 4 electrons form a covalent bond? Yes, the answer to that is absolutely. So yes, carbon and anything with more than 4 valence electrons has a tendency to form covalent bonds. What about fluoride? Right? Let's think about fluoride for a minute. So go ahead and draw the electron configuration for fluoride. And if we think about that based on our periodic table, what should we see? Go ahead and draw the orbital diagram and the electron configuration for fluoride. So in this case, if I'm thinking about fluoride, I should have something that looks like this, right? So I want you to think, is it easier for fluoride, right, to give up those 7 electrons or to gain 1 electron? There are 2 ways that it can gain an electron. It can form a covalent bond, in which case it would share its electrons, or, right, it can gain an electron from an ion. So for example, sodium fluoride. Sodium could give up its electron and give it to fluoride, in which case fluoride would then have a complete octet. So I think, hopefully, what you've seen here is that when we're writing orbital diagrams and electron configuration, that starts to show us how our atoms are going to react with each other. And the reason why that's super important is because all of our chemical reactivity is going to be based on our understanding of the number of valence electrons and how those electrons might behave. So if you think about this, right, the other questions that one could ask, well, let's think about, say, for example, carbon versus nitrogen versus oxygen, right, and why it might have that behavior. So there are some other questions for you to think about answering here. If you're like, ooh, okay, I feel like I'm pretty solid there, but I think I still need some additional practice, here's my suggestion. If you take a look at our learning plan for today, so we did our prior knowledge, the practice with ionic formulas. That's something that you absolutely can go back to and finish up. In fact, I highly recommend it because that's going to be a skill that I'm just going to assume you know how to do on exam 2. For the phenomena, for the station for the flame video, this is really what we showed so that you could make sense of why we start to see some of the changes that we do. Why we see the colors, say, for example, that chemicals contribute to the world we live in. Being able to do an electron configuration and being able to determine valence electrons is something that I'm going to ask you about on Wednesday's quiz. Now you're like, wait a minute, we're going to have a quiz? How are we going to do that? Well, I'm going to introduce you to a tool on Wednesday called Flipgrid. So Flipgrid is one of the ways where you can write out and then post a short video of your response. And that's the way we're going to test out and do our quiz on Wednesday. Ooh, so somebody asked about the electron configuration for fluorine. So here's the orbital diagram for fluorine. You're going to notice that the electron configuration is 1s2, 2s2, right? 2p5 is the fluorine atom. The fluoride anion would have the electron configuration of 1s2, 2s2, 2p6. So the virtual plans are in an email from me to you. So if you look at the most recent email from me to you, you should be able to find that. So there's a video invitation to the Zoom lecture from today. And then if you look at the email right before that, it has our plans for today. And I'll post these as a URL on iLearn as well. Here's what I want you to notice. On the right-hand side are some optional virtual supports. So these are some additional videos that if you're like, hey, I'm still trying to make sense of this, I could use a little bit more support, are resources that I recommend. So where does that leave us? Well, on Wednesday, you're going to do a quiz for electron configuration. And if you want to practice, right, to make sure that you are comfortable, I will choose an element from the first 3 rows. Right? So the first 3 rows, I could choose an element for you from the first 3 rows. So those are great electron configurations and orbital diagrams to practice. And then if you're thinking about this claim evidence reasoning, I'll go ahead and post up the key to these later on today. Same thing for both of these. By the end of today, I'll have keys for all 3 of the worksheets we did in class, plus the prior knowledge. So we are at the end of class today. If you have any questions, I will happily stay on for the next half hour or so to be able to do individual questions. So at this point, I'll unmute you and you can ask any question that you like. If you're like, hey, what about this? I'm still confused, then please don't hesitate to ask, and I'll post the video as soon as we're done. All right, how can I help?
I never got the, I was never able to see the configuration for fluoride.
That's because I think my video will flip this screen, so I'm gonna call it out to you, right? It's 1s2, 2s2, 2p5 is fluorine, the atom, right? Fluoride, the anion, is 1s2, 2s2, 2p6. So it becomes F- and it gains an electron.
Thank you.
Lauren, it actually shows them the correct way. When you're showing the thing on their screen, they see it the correct way.
Oh, how delightful. Like, I kept looking at it, I was like, oh man, really, it's flipped? Ah, thanks,
Yeah, so
Jess.
for you it looks flipped. For everybody else looking at it, it's the correct way.
Oh,
So
hooray.
that's why
Okay,
she's
well, then I'll
telling you
just
like
write
she
it out.
can't see it. Because you have it like 2 down also, so you're not actually showing the screen.
Oh, gotcha. Hold on. Let me hold it up higher then. Okay. Can you see it now?
I still see the virtual plan sheet.
Ooh, okay, hold on.
How do I do that? Oh,
Okay, can you see it now?
yes. Thank you.
You are welcome. Cool.
I have a
Other
question.
questions? Oh, sorry, I should probably hold for a minute longer.
I was wondering, how do you know the configuration for fluoride compared to fluorine? Like
Yep, Great question. So in this case, right, fluorine, right, just F is what you would know as the electron configuration from your periodic table. So if you know
Right.
the periodic table, its atomic number is 9,
Mhm.
right? So I fill the first 2 electrons in 1s, the next 2 electrons in 2s, and then that means I've got 5 electrons left. So that's the reason why I fill the 2p with 5
Mhm.
electrons. So singly, and then I pair up 2. And then, right, if you're thinking about the fluoride ion, it's going to want to gain an electron so that it has a complete 2p. So you're going to fill up pairs of electrons, right? So we're going to add 1 more electron, and that's why it's F minus.
Okay, that makes sense. Thank you.
Yeah, good, sweet. Okay, other questions?
For copper and chromium, could
Yep.
we still be able to get the long and short version from just counting the like elements across each other, or do we have to actually do the configuration first?
That's a good question. So you can do the configuration for them, and actually I recommend you try that, because I think what's likely going to happen is you're going to do the configuration and you're going to be like, wait, that's not what she has written. And that's the reason why there's an exception. So if you write it out the way that we've been training you to write electron configurations, you're going to get the wrong electron configuration. That's why there's exceptions. And so that's the reason why I included them in the class today, is not because I expect you to memorize or know the exception, but because I think seeing the exception helps you understand why you fill them differently than you would any of the other atoms.
Okay, yeah, that makes sense.
Okay, what else can I do?
Can you explain the ionization energy on how that the chart that
Yeah.
had
Mhm.
beryllium and
Yep.
boron?
So let me share. There's actually a better one at the bottom of the learning plan. So if we scroll down, go just a little bit. Okay. Can you see that better now? So these are ionization energies. And if you think about it, right, what's along here is the energy that it takes to pull off an electron. So it makes sense that helium would have a really high ionization energy because it's paired electrons. They're already paired. It's a complete octet, or in this case, it's a complete shell. So that first shell only ever has 2 electrons. And so because those 2 electrons fill the first shell, helium is completely satisfied. So its ionization energy is going to be really high. Then, right, this block between lithium and neon, that's the example that we were looking at in our notes here, right? So I just expanded it so you could see it a little bit better. And the reason why that matters is because, if I go back here for a minute, right? If you think about it, lithium has the lowest ionization energy because it's the closest. All you had to do was take 1 electron away, and then, right, you are essentially back to helium, which is really stable. So if I just remove 1 electron from lithium, then I'm back to helium, right? But neon is a lot like helium in that it's a noble gas. So it takes a lot more energy to pull an electron away because this is a stable configuration. And so when you're thinking about ionization energy, all it's really telling you is, hey, helium is very stable. It doesn't want to give up any of its electrons. Whereas lithium, sodium, potassium, rubidium, cesium, franconium, like these are all atoms that are willing to give up 1 electron, which is why they're so reactive. Right? Each of these give up a single electron. That's why we see them as lithium plus, sodium plus, potassium plus in nature, because these are very willing to give up their electron. They're super reactive. Does that make sense?
Yeah, I'm
Yeah?
just I'm just so confused why about the boron and beryllium,
Uh-huh.
because boron has a higher ionization energy.
Mhm.
So why is that it's less than?
Yep. So let's actually draw that out, and then you'll be able to see the difference. So I'll do it on my whiteboard, and you can do it in your notes. So let's draw out boron and let's draw out beryllium. How about you do boron and I'll do beryllium?
The electron configuration or
The orbital diagram and the electron configuration. Okay, you ready? So here's what I've got for beryllium. So if you think about it, right, beryllium is super stable, right? It's got two, right? It's one S is filled and it's two S's filled. How does that compare to boron?
Boron has an electron on the 2p.
Uh-huh. So boron wants to give up that electron in the 2p, right? It's easier to remove that single electron. That's why it has a lower ionization energy.
Okay, so then as we go across the period, it's decreasing?
Yes and no. So if you're just at the very beginning of a period, it's going to have a lower ionization energy because it wants to get rid of those single or maybe two electrons, right? But then as you go further across a period, in the middle it kind of gets squishy, right? Because at that point then the nuclear charge takes over and it pulls harder on electrons. And so as you go across a period, that's where you start to see the change. So for example, if I go back to the I go back here, all right, see how there's a hitch, right? So, right, lithium, beryllium, boron, then, right? So beryllium is going to have a higher energy than boron, right? Because of that S2. And so if I'm thinking about here, right, here's beryllium, here's boron. Beryllium has a slightly higher energy, right, because it's already got paired electrons in an orbital. Whereas boron has one single electron that's in an orbital by itself. So it has a slightly lower energy because it's willing to give up that single electron to go back to having two electrons that are paired. Better?
Yeah,
Awesome. Okay, other questions?
thank you.
So my Wi-Fi cut out for the first hour of the lecture and I wasn't able to hear anything.
No worries. I'm recording it and I'm going to post the recording and you can kind of scan through. If there are specific questions you have, I can answer them too.
How do you know everything? How do you know how many electrons there are in each row?
Ooh, that's a great question. So in terms of electrons in a row, right, the 1s always has 2. The 2s always has 2. And then 2p will always have 6. Anything that's d will always have up to 10. And anything that's f will have up to 14. And that's based on the capacity of those orbitals. If you're going across the row in terms of a periodic table, then the way that you make sense of that, right, is the number of periods, right? So those are your rows, right, versus the number of groups, those are your columns. And so if you look at the top of a group, that tells you the number of valence electrons, but you'd have to look at the atomic number to know the total number of electrons for any given atom.
So do you just kind of fill up like each row as you go, like
Exactly.
electrons? Okay.
Yep, that's exactly the way that I do it.
But then the valence electrons are what comes last. So you like fill up everything else. And P has up to 6?
Yes, so P can
It
fill
always
up
has
to 6.
Okay, and D was up to 10, right?
Mhm.
Okay.
Okay, so if we're thinking about the kind of just general structure, you can always think of orbitals as capacity. So I think of it as like garage, right? A garage can fit 1 or 2 cars. So the s orbital can fit 2 cars. The p orbital would be like a 6-car garage. The d orbital would be like a 10-car garage, and the f orbital would be like a 14-car garage. That doesn't mean that you always have 14 electrons in the f orbital. It just means it can hold up to that many. And so we always fill then electrons based on the atomic number of whatever atom we're working with.
How do you know which number, like for, I think it was sulfur, there's 3s2 and 3p4. How do you know that that's a new? Oh, because the first ones were filled up with 8, so then you like add a next number and more electrons.
Yep,
Okay.
you got it. Other questions?
So from classes starting forward from now on, how is this different from like our regular lectures? Are we supposed to take like extra preparation for stuff or?
So here's what I was thinking about. I was trying to figure out a way to do this because I realize that lots of folks have questions, and sometimes the ability to ask and answer questions with practice is better. And so our class will be exclusively practice. The videos that I posted are a great way to summarize the reading that you're doing. So if you're reading chapter 6, the videos that I post ahead of class is a great way to check in and make sure that you have a correct understanding of that reading. So I don't think it's really all that different than us meeting in person, other than I'm trying to provide video summaries of the reading to help make sense of that for you before you come into lecture. So a couple of folks were like, yeah, sometimes I do the reading, but it doesn't always make sense. And so that's the purpose of those videos. If you've done the reading, you can just come straight to lecture on Monday, and we'll be solving problems that are examples based on the reading. Does that make sense?
So yeah, so basically just the classes and then the videos.
Yep.
That's our like preparation for each lecture time.
Yep, you got it. And then we'll do discussion like we normally would, except it'll be a Zoom session, and I'll break you out into smaller groups to work on the discussion worksheet.
Okay, thank you so much. That makes sense.
Yeah, for sure. And that's part of the reason why I think having the whiteboard is super helpful, because then you're able to show, right, this is how I made sense of what it was I was doing. So if you don't have one of those, just let me know, and I will send it in the mail to you, snail mail.
Okay, thank you.
You're welcome. Thanks, Julian. Great question. Other questions?
I wanted to know about the exam too, how it's gonna work.
Ooh,
or like,
great question, Kathy. Yep. So here's what I've decided. I feel like at this point, exam 2 is really making sense of what you know. So I've decided that I will do exam 2 as open resource. You can use your book, your notes, anything that's available on the computer. And essentially what I'll do is I will post the exam, so it'll be open for a 2-hour window, and then you're going to email it to me when you're done. So you'll take screenshots of your solutions and you'll send me an email. So I think that's the easiest way to do exam 2. And I decided that I was going to shift that until after spring break. I feel like everyone's got a lot of change under their belts this week, and so that probably wouldn't be the best way to approach this. So we'll do exam 2 when we come back from spring break, after we've had a chance to do a little bit of review. And then the Wednesday class period where we would normally have classes, when you would do that.
What topics is exam 2 going to be mainly focused on?
So it'll be everything we've covered so far. So all exams are cumulative.
Mm-hmm.
So it'll be chapters 1 through 5 and 6, which is what we're doing right now, and chapter 9.
Okay, thank you.
Yeah, you're welcome. Of course, my pleasure.
Corinne?
Okay, anything else? Amber, how are you?
I'm good.
Oh,
I
I'm
have a
glad to hear it.
About one of the, I don't remember which element you did, but you filled in the, I think it was, I don't remember, but you filled in the top one before you filled in the one below. How come you did that? For the electron configuration?
Yep. So I can take you back. This is an exception to the electron configuration rule. So there aren't very many atoms that are exceptions to the electron configuration rule. Most of them all follow the rule. But the example that we did in class, I'll pull up. Give me 2 seconds.
It was chromium and copper.
Yep.
You said.
So if I go back. So this example, so here, right, you were asking why I filled this one before I filled this guy, right?
Yeah.
Okay, so in the case of copper, the reason why I do that is because there's a rule that says that anything that is completely filled or is half filled is more stable than something that's only partly filled. And so you'd be tempted to do the electron configuration for this guy where this is 4s2 and this would be 3d9. The problem with that is that 3d9 is less stable because one of these electrons is unpaired. And so instead, it's better to completely fill all of the 3d electrons so that everything is paired. And then the 4s, right, we have half filled with a single electron. And so that, I think, makes it more stable because this is half filled and completely filled. Whereas if you drew it out the way you would think it would look, right? So you'd be tempted to draw it this way. Hold on, I'm gonna post it in just a minute. So you might be tempted to write it this way. So if we were writing it according to our normal rules, it would probably look like this, right? Where the 3d9, right? That's what we would expect to see if we were following our normal rules. But it's more stable if instead of having that S filled, it's better if we move the electron from that 4s over to the 3d. So now it's 3d10 where the d orbitals are completely filled and the s orbital is only partially filled. Does that help, Amber?
Yes.
Okay, cool. All right, other questions?
I have a question very similar to Amber's.
Yeah, go for it, Mackenzie.
So, like, I kind of like drew it out. I don't know. Can you see it now?
Let me see.
Yeah. So like, do we fill up all the 3s first before the 4? Like how, like in the last one? So we have to fill up the 3D before we go to the 4S?
That's correct. Mm-hmm.
Okay.
And if you think about it, right, when you're looking at, so let me find a good example to show you. Hold on. If you're looking here, for example, do you see how there's not a big difference between the 4S and the 3D? Mm-hmm. They're really close in energy, right? So I could fill either one of these pretty much at the same time, right? It's not hard to transfer electrons between them, right? But the 4P actually requires more energy. So I would have to put more energy in order to be able to fill the 4P. So that's the reason why we always start at the lowest floor and we fill here and then we fill up as we go, because we only have enough energy to put the electrons in whatever the lowest orbitals are for the most stable compound.
So if we had like an electron with a whole bunch, or an atom with a whole bunch of electrons, would we have 4D and 4F as well?
Mm-hmm. That's correct.
Okay.
So you could easily have, and granted, I don't think it gets tedious to write out all of those, right? So I'm not going to ask you to do that, but in principle, yes, that is what you would see. So for example, if you were writing out the electron configuration, in fact, let me see if I can find, there's a really cool, I'll post it. There's a periodic table that actually has the electron configurations. I'll post it to iLearn, where in each box it lists the electron configurations, but the boxes get really tiny after a while. But yeah, you're spot on. So you're always going to fill 1 and then 2 and then 3 and then 4.
Okay.
Other questions? What else can I do?
Do valence electrons always have their own like set of numbers? Like even if you don't fill up the ones before it?
So I think I understand what you're asking. And the short answer is it depends. So for example, let's do carbon, right? If I think about carbon, so if I think about its valence electrons, right? So I'm going to fill up the 1s, I'm going to fill up the 2s, and then, right, for carbon, right, my total number of electrons is 6. So it should look like this. So its valence electrons are the 2s and the 2p, so a total of 4 valence electrons. So the valence electrons are always whatever the highest number is that's to the left.
Okay.
Does that help? Was that your question?
Yes and no.
Okay.
I don't know. So like, even if you don't fill up like 1 and 2, like say 1s2, 2s2, 2p4,
yep,
something like that, would valence electrons fill up like the rest of the 2p6?
So you can think about it this way, right? So carbon has the ability to form 4 bonds. So if I think about it, right? So here's carbon, right, with its 4 valence electrons. Those valence electrons are these 4.
Okay.
Okay. If I were to form a bond, say for example, between carbon and hydrogen, that would look like this. So that's an example of methane. And that meant that some of the time, right, those electrons would also be with carbon, because that's the definition of a covalent bond, is that you share the electrons. So then if I think about it, for methane, right, the reason I can form methane is because part of the time, the electrons from hydrogen satisfy carbon to give it a complete octet.
Okay.
All right, other questions? What you got?
I wanted to know about the electron configuration for the anions and the cations, like how
good
that
question.
works.
That's a great question. So let's choose one. Which one do you want to do first? Do you want to do sodium as a cation, or do you want to do an anion first?
Sodium is fine.
Okay. So if you pull out your notes, I want you to go ahead and draw what you think the electron configuration and orbital diagram for sodium would be. Okay. So if you take a look, right? So sodium's electron configuration would be 1s2, 2s2, 2p6, 3s1. So it really wants to give up that single electron, because then what does it become? If sodium gives up one electron, what does it become? It becomes like neon that has a complete octet. So if it gives up that one electron, instead of being 11 electrons, it becomes 10 electrons. And we know that neon is a really stable noble gas. So then neon, right, just stays, right? It doesn't want to give up any electrons. So by giving up that one electron to form sodium positive, right, that's the same thing as sodium becoming like neon.
Okay.
Better?
Yeah.
Sweet. Okay, how about you do it for chloride? Show me what you got.
Wait. Would it be 3p5?
Yeah.
Bless you.
Bless you. Okay. So it would be something like this.
Mm-hmm.
right?
I got the first one. Yeah.
Yeah?
So when it's Cl minus, you add one to it.
Mm-hmm. So if it's an anion, you're adding an electron.
Okay.
So if it's a cation, you're taking an electron away. If it's an anion, you're adding an electron.
Okay.
Great question.
Why don't you have 3D on there?
Because I don't need to draw it in this case, because for chlorine, I don't have that many electrons, right? I could, right? So for example, one of the ways that I try to make life just a little bit easier for you on the notes is to give you kind of the prompt to show you what that looks like. So for example, when we're practicing on Wednesday's quiz, I might give you one to kind of help you get started. But the best, I think, example of the type of questions that you'll see on an exam would be ones that look like this, from the later practice that we did, where something like this. So that's, I think, what you're most likely to see on an exam. So you only have to draw as many as you need, I guess, is the short answer. Right? Because technically those orbitals always exist. You could put electrons in them. In fact, one of the things that ends up happening is there are folks that do really cool chemistry looking at what happens when you excite electrons up in the higher energy levels and then they relax back down. And those are the colors that you most commonly see, say, for example, in fireworks. But you don't always have to fill those orbitals. They exist, but you don't always have electrons in them. So my recommendation is only draw as many as you need. You don't have to draw more than that.
I just want to make sure I'm getting this correctly.
Of course.
So if, like for example, like Cl minus, that's an anion, right?
Yep, that's correct.
But there's one more electron.
That is correct. So it adds an electron.
So if it's an anion, it adds an electron.
Always. Which is why it gets that negative charge, because it has one more electron than it would have if it was neutral.
Okay, thank you.
You're welcome.
I have a question.
Of course.
So when we're adding one electron, does it mean you want us to add it to the drawing?
That's correct.
Okay.
So to your orbital diagram and to your electron configuration. So for example, if I ask you to form an anion, you're going to add an electron to both your orbital diagram and to your electron configuration. If I ask you to form a cation, you're going to take an electron away from both your orbital diagram and your electron configuration.
So do you want two different, like one before and one after, or do you?
So for the purposes of, say, for example, a quiz or an exam, I'll be really clear. I'll probably ask you to draw one, right? And then to draw the other. There'll be two separate parts, like a part A and a part B.
Okay. I just want to make sure that, like, if I put 8 valence electrons on the outer shell, that I wouldn't get docked if, say, it was chloride.
Yep, if it was fluoride, that would be the correct way to answer that question. Yep.
Okay.
Yep, you're good. Other questions? Jess, I wanted to say thank you for hosting the Zoom S-Cube sessions last week. I know you didn't have to do that. It was awfully kind of you to offer to do so. I really appreciate it.
Of course. I'm here to help everybody, so.
You are amazing, and we are so thankful for you.
I'll also be available spring break too, so if people want help over spring break, it's not required, but I will also be available for that.
Oh, you are such a rock star. Thank you, thank you, thank you. All right, any other questions, folks? Yeah, go ahead, Amber.
Transition metals. Can we talk about that one more time?
We
the
can.
Whole D section.
Yep. So let's do one. For example, let's do, you pick one. Pick one in the 3 row.
In the what?
In the 3rd row. So technically, when you're looking at your periodic table, the 3Ds start in row 4. So where you see potassium and calcium, that first row of D metals are the 3D metals. So the ones that begin with SC, TI, V, choose one of those.
Okay. Iron?
Sure, let's do iron. It's a great one to do. Sorry, I'm erasing my whiteboard. I think I just need to like have 3 in doc, so then I don't have to spend so much time erasing. Things you learn as you go. Okay. I'm drawing. Thank you for your patience. All right. Okay. So, can you see? So in this case, right, you fill the 4s2 for iron, and then the 3d6, right? So you fill each of them singly, and then you pair one, your last electron, in one of the d orbitals.
Why is it 3d6?
Because if we look at the total number of electrons, we have 26, right?
Yes.
So, right, we fill the 4s2 because we can fill that completely, and we want something that's completely filled because that's more stable. But we don't have enough electrons to completely fill the d. We only have 6 electrons remaining, and so we fill each of the orbitals with 1, and then our last electron we pair up.
I have a question.
Go for it.
So for the transition metals, do you always do the 3D section?
Yep. So for transition metals, you're always going to have a D section that you're filling. The really good news is that on an exam, I think it's going to take too long to have you do transition metals. So likely what I will probably do is give you a transition metal electron configuration and then ask you to tell me what kind of ion it would form. Does that make sense? So rather than having you have to write out everything, I'll probably give you the electron configuration, and then say, for example, for iron, I would say, how would the electron configuration change if you formed iron 2+?
Okay.
Okay, I'm still a little confused, and
Go for
it's
it.
because I put 4s2 and then 4d10.
Okay, so if we count, right, our electrons, because we have 26, so we have 2 that go in 1s, 2 that go in 2s, that's 4, 6 that go into 2p, that's 10, another 2 that go into 3s, right, so that's 12. Our 3p, right, has 6, so that's 18. And then our 4s2 would have 2, so that's 20. And then we have 6 electrons remaining. And so those 6 are what go in the 3D.
So it's not called 4D, it's called 3D?
Yep. This is why it's super goofy, right? So the d orbitals are always 1. So that row that says 4, right? Only for D, the atoms that are there are 3D. And the reason for that is because the D's are so close in terms of energy to the 4s. So that's the reason why. When you're looking at your periodic table, that middle section that are your transition elements, it's always the number that's 1 less than whatever row it is. So for example, if you're in row 4, the D's are always 3. If you're in row 5, the D's are always 4.
Okay, so that would be the scandium, titanium, vanadium.
Yep, so that's the 3D transition metals.
Yeah, and can I see the whiteboard one more time?
Yeah, for sure. Sorry, I'm trying not to smudge it with my fingers.
Okay, that makes sense. Thank you.
Better?
Yeah.
Sweet. Okay, any other questions?
So we don't have to lose. We don't have. I'm sorry, Mackenzie. We don't have to lose any electrons or gain any, right?
Nope, because it's just iron by itself. If it were to form a cation, say for example, iron 2 plus or iron 3 plus, then you would take electrons away. So if it was iron 1 plus, it would look like this. Sorry, erasing. So if it was iron 1 plus, it would look like this. Right, where I took one of those electrons away.
Oh, okay, I see.
Yeah, sorry for the light. Other things I will learn how to change. Okay, and Mackenzie, you had a question?
Yeah, I mean, I'm still just kind of confused on when to fill in 4S first and then when to fill in 3D. So do you fill in the one that you can completely do? So like if it were to have been 30 electrons and we could have completely filled in that 3D, then would we have done it that way?
Yep, so let me show you a trick. This is always how I remember what order to fill, and it will make your life so much easier. So if you start out and you write out just the column, right? So the 1s is your first column, and then you drop down one and you start the 2p's, and then you drop down one and you do the 3d's, right? And you draw out that triangle. Then once you have that triangle, while you guys are drawing that, then I'll show you what to do with it. Then you draw these arrows. And these arrows tell you the direction that so you always fill 1s first, then you fill 2s, then 2p, then 3s, right? Then 3p, then 4s, then 3d, and so forth.
Oh, okay.
So it's a really easy like device to help you keep track of which you fill first. Does that help?
Yeah, so that's why like 4S you fill before 3D.
Exactly.
Of the arrow. Okay.
Yep. And this is the order of filling. And there's some math that's the reason why we have this order of filling, but that math is outside the scope of this class. So all you need to know is the correct order for filling.
Okay. Thank you.
You're welcome. Other questions? All right. So I know that S Cubed has a session this afternoon. Thank you, Jess. And I also know that we have additional online virtual office hours from 2 to 4. So I'll just be hanging out on that Zoom link. If you've got questions or the things you're working on, just let me know and I will help out as best I'm able to. Everybody good? Any other questions before we go?
You said the cations, is it that when you add?
The cation is when you take away, the anion is when you add.
Okay. Thank you.
Yeah, no worries. Anything else?